Okay, so now that we've learned how to compute eigenvectors and eigenvalues for square matrices, we are going to use that insight to help us solve systems of linear ordinary differential equations, so-called linear systems. And we're going to stay in the sort of constant coefficient homogeneous case for this discussion, okay? But you're going to see the eigenvectors stuff that we learned is going to come in real clutch and be central to what we do. So just as a reminder, well, let me title this first. So eigenvector method for solving systems. I'll just call it x prime equals px, right? Because this is the form, remember, that our system of differential equations takes, where p here is an n by n square matrix. And remember, we make a guess about the solution, the ansatz, as it's called. The ansatz, the guess that we make, is that x looks like v e to the lambda t. Our solution looks like some vector v times the function e to the lambda t for some value lambda. And what this ends up giving us, what this ends up, you can work it out, what this ends up telling us is that v ends up being a eigenvector. So this is a solution, I should say. If v is an eigenvector of p with eigenvalue lambda. Okay, so what this is going to allow us to do is use the eigenvector stuff that we learned about to find solutions to this to the system of linear equations. Okay, so let's do a simple example here first. Let's find, for example, let's do the following system. Let's do x1 prime is equal to 3x1 plus x2. I'm just getting this straight from the textbook. And x2 prime is equal to 2x1 plus 4x2. Okay. So our first step is going to be to translate this into this form. X prime equals px. Well, of course, x is itself going to be just x1, x2. It's going to be a 2 by 1 vector. Okay. And x prime then is going to be the matrix 3, 1, 2, 4 times x1, x2, which is just x. Sorry, I should just write x here. So, of course, what I'm saying here is that this is my p in this case. P is this guy right here. Okay, clear so far? How did I get 3, 1, 2, 4? How did I get that matrix P? I just looked at the coefficients in order of x1, x2. In the first equation, those became my first row, and of the coefficients of x1 and x2 in the second equation, and those became my second row. Okay. If I had more equations or more variables, then you would expect the matrix to expand and be bigger. But we have two equations in two dependent variables, x1 and x2 here. Okay. All right. So the ansatz says that we should try guessing that the solution looks like v times e to the lambda t. And it's a solution if v ends up being an eigenvector of p with eigenvalue lambda. So what we should do is find the eigen pairs, the eigenvalues together with the eigen vectors of p. So we're going to find eigenvectors of p. Find eigen stuff. Find eigen stuff of p. Okay, so we've talked a lot about how to do this, so this should be more or less reflexive at this point. What we're going to do is first find the characteristic polynomial. The characteristic polynomial, remember, is the determinant of, in this case, p minus lambda times the identity, the 2 by 2 identity. So that's the determinant of 3 minus lambda, 1, 2, 4 minus lambda. And I know you can compute this. This is 3 minus lambda times 4 minus lambda minus 2. If we expand this out, this ends up being so 12 minus 7 lambda plus lambda squared minus 2, which if I write it in descending order as I like to do, I get lambda squared minus 7 lambda plus 10. I hope that's right. Oh, and we can observe that this thing factors, right? This thing factors as lambda minus 5 times lambda minus 2. Okay? So what this tells me from the characteristic polynomial is that my eigenvalues are the roots of the characteristic polynomial. But now that we have it in this nicely factored form, it's easy to read off the roots. The roots are 5 and 2. So we have 2 eigenvalues. So in other words, these are the numbers, these are the values that are going to appear in the exponential, right? Okay, cool. Let's find eigenvectors, v, associated to each of these eigenvalues. So we have to do each one separately. So we'll start with lambda equal to 2. So when lambda is equal to 2 here, I'll do this in green. Lambda is equal to 2. Let's do that one. I don't know why I did 2 first. Whatever, it doesn't matter. So what I want to solve is the equation p minus 2 times the identity times v equals 0. Okay, why 2 times the identity? Because lambda is equal to 2. That's the assumption that we're working under. Now I'm going to form an augmented matrix as usual. So what we get when I put in 2 for lambda, and I can just look right here, that's p minus lambda times the identity. And if I replace lambda by 2, what I get is, of course, 1, 1, 2, 2. And then if we augment with zeros, we're going to get something like this. Now, listen, you've done this enough now, and it's just a fact. Okay, fact. Here's the fact. If the determinant of A is 0 and A is 2 by 2, so in the special case where A is a 2 by 2 matrix, then row 1 is always a scalar multiple of row 2. This is a fact, and I will allow you to just use this fact without mention. Why is that so? Well, you can think about it. If you start with the condition that the determinant of a 2 by 2 matrix is 0, you're going to see that that sets up a kind of relationship between between the entries of the matrix, which necessarily implies that the first row is a scalar multiple of the second row. Okay, but we see that manifestly in this matrix here. I guess I'm really looking at this first part of the matrix. This comment really applies to this part of the matrix here. Point being, though, because this the augmented bit will never change, it's still going to be the case. What I'm saying is, when you put in this eigenvalue 2, because that 2 makes the determinant of p minus lambda I equal to 0, the first row will always be a scalar multiple of the second row when we're dealing with two-dimensional systems. Okay? In particular, what that means is that we hardly have to think. We don't even have to do row reduction if we don't want to. We can leap from the matrix, which tells us the relationship between v1 and v2, because we know that the second equation will always be redundant. So we can just use the fact that we see v1 plus v2 from the first row is equal to 0. I hope you understood my comment. Now we need to find a vector v1, v2 which satisfies this constraint. And it's pretty clear, is it not, that 1, -1 does the job. So V equals 1, -1 is an eigenvector. I'll just write E vector with lambda equals 2 in this case. Okay. Second point. Second eigenvalue is lambda equal to 5. Let's do this in purple. Okay. So now we want to solve, in this case, p minus 5 times the identity times v equals 0. We want to find a non-zero v, which makes this happen. So if we plug in 5 into this matrix here, I'm looking right here. If we plug in 5, what we get is -2, 1, 2, -1. Oh, and I augment with a 0, right? Again, you see that the second row is a scalar multiple of the first row. So there's no new information provided by that second row. What we learn from this is that -2 v1 plus v2 must be 0. So we need a vector v1, v2, which satisfies this condition here. And we can take, I don't know, v1 to be 1, which would make v2 be -2. No, +2, my bad. I vaguely know what I'm doing. Yeah, like this. And this is an eigenvector with lambda equal to 5 in this case. So that's nice to know. I'm boxing these because these are important for my for me solving the problem. Don't forget what the problem is. The problem is to solve this system. Now that I've got my eigenvectors and my eigenvalues, I can write down solutions. And in fact, these eigenvectors, you can see already, are linearly independent. I mean, there's going to be linear independence, frankly, coming from the ansatz as well. Let me not talk. Let me just write things down. So, for example, I can make x1 be, don't forget the ansatz, it's v e to the lambda t. So v in this, I'm going to look at the first eigenvalue first, so that's lambda equal to 2. V is 1, -1. We multiply this by e to the 2t. This is a solution. Another solution is x sub 2. I'll call it x sub 2. All right. And this is going to be v e to the lambda t again, but now using lambda equal to 5. And the associated eigenvector is 1, 2, e, and then we have e to the 5t. Okay? These are solutions. They are linearly independent. And I can tell you that whenever you have distinct eigenvalues, if you have two solutions coming from two distinct eigenvalues, you're going to get linearly independent solutions. Things get complicated here where if you have, there are complicated things that we could say. So we want to concentrate on the distinct real eigenvalue case. We have distinct real eigenvalues here because, well, these are real numbers, lambda equal to 2 and 5. They're real, but they're also not equal to each other, okay? Things would get more complicated if we had, I'm not even sure if we're going to get into it. We might, okay, when we talk about repeated eigenvalues, okay? But let's put that very complicated issue off to the side. For right now, we have two distinct eigenvalues. And so it's just a fact, okay? Maybe I'll write this fact right here. Fact. Solutions from different eigenvalues will necessarily be linearly independent. Ooh, linearly independent. The very important fact that, I don't want you to sleep on it because it's important. It's going to motivate some of the stuff that we have to deal with later on. So don't sleep on it. But in particular, what this means is that for this two-dimensional system, x1, x2, this system here, we know that the solution space is going to be a superposition of two solutions, right? This is a homogeneous system. So we can write down the general solution to this problem. The general solution is going to be a superposition of x1 and x2. So that's c1x1 plus c2x2. And we can write this out, if we want to, as c1 times 1 negative 1 times e to the 2t plus c2 times 1, 2 e to the 5t. You see what I've done? All I've done is transported this x1 to here, and I've transported this x2 to right here. Okay? And then I put c1 and c2s in front of it because I need a general superposition. What I'm saying, and I'm right, is that every solution to this system right here is given by this expression for some choice of C1 and C2. And vice versa. Every choice of C1 and C2 gives rise to a solution to this system here. Do you believe it? Well, you don't have to. We can check it, okay? We can check it. And I will do this once in my life for you. Well, I'll probably do it many times in my life, but I'll do it once this semester. Yeah. Let's do it. Let's do it once at least. Check. Okay. Let's check, for example, what happens if we let C1 equal, I don't know, 2, and maybe C2 equal, I don't know, 3. So we're going to fix values for C1 and C2. I don't know why I'm doing it this way. I just want you to see something very concrete. Then what we get is that x, our proposed solution in this case, is going to be the vector 2, negative 2, e to the, e to the 2t plus 3 times 1, 2, which is 3, 6, e to the 5t. Now, if I like, what I can do is write this as a single vector, right? I can write this as a single vector by adding the first components of the vector together. And I get 2e to the 2t plus 3e to the 5t, and then adding the second components together. So I get negative 2e to the 2t plus 6e to the 5t. Do you believe? Okay. So that's my x. Now what's x prime? So x prime, I'll write it here. X prime is going to be what I get by taking the derivative of that, and that's easy. That's 4e to the 2t plus 15e to the 5t, and downstairs we have negative 4e to the 2t and 30e to the 5t. That's x prime. Okay. Now, what is, so I need to look where? P times x? Where's my, yeah, here's my P. It's 3, 1, 2, 4, don't forget. So P, don't forget, is 3, 1, 2, 4. So what should happen is if I compute P times x, I should get the same thing that I have for x prime. That's the whole point. X prime should be equal to P times x. So let's compute P times x. So that's the matrix 3, 1, 2, 4. And we're going to multiply this by the 2 by 1 vector that I've got here. In fact, what I'll do, because I feel like I should be taking advantage of technology in some way, is I'm going to take this thing here, I'll duplicate it, and then move it right here. Okay? Neato. I have no idea if that was worth it, but I just did it. Okay? So what do I need to do? Don't forget, I need to multiply row by column. There's only one column here, okay? Here, I mean. So I'm going to do this row times this column to get my first entry. So this is going to be messy, but we're going to deal with it. So I'm going to 6 e to the 2t plus 9 e to the 5t. So that's the 3 times the first entry, and then 1 times the second entry, which is negative 2 e to the 2t plus 6e to the 5t. Okay, cool. So that's the first entry of px. The second entry of px is, don't forget, this row times this column. So what I obtain is 4e to the 2t plus 6e to the 5t minus 8e to the 2t plus 24e to the 5t. Oh God, right? But what I can do is collect like terms to make this look nicer. If I collect like terms, so like in the first row, how many e to the 2t's are there? There's 4 of them. 4e to the 2t. And how many e to the 5t's are there? Well, it looks like there's 15 of them, 9 plus 6. And then look down here. How many e to the 2t's are there? Looks like there's negative 4 of them. And how many e to the 5t's are there? It looks like there's 30 of them. I feel like I'm having deja vu. Why is that? Oh my God. Because it's this. I just wrote that again. Look here. Look at this matrix. What was this again? This was x prime, right? And look at this one. That's p times x. So what we see, evidently, with our eyeballs, is that x prime is equal to px. Okay? Does this make sense? Okay. This is the method. We're going to do a 3x3 example in the next one. I mean, it's important for you to get practice doing all of this eigenvector, eigenvalue stuff. So, again, I don't feel bad. I have no shame. I can't apologize. This is good for your health. Okay, bye.